put my son on the internet if I can help it. But I gave you an email yesterday in which I told you I posted something new, so just in case you haven't had a chance to check that yet, based on my informal survey at the end of our last class, I decided we're going to do a little more on interaction terms than I had planned for. So I put up some slides that I have revised that were in my version of intermediate here as Lecture 1 bonus, and we'll work through Lecture 1 today and Lecture 1 bonus. And if we're feeling ambitious, maybe we'll get to Example 1. Who knows? We'll see. We'll see where the day takes us. Feeling spontaneous here. All right, so what did we do last time? What are we talking about? Any vocabulary words you remember? Centering. Yeah, what's centering?
It's where we readjust where we want the zeros of our data to be in order for them to make more sense in the context we're using them.
Yes, we readjust. We rescale our predictor variables so that 0 is included within the observed distribution of the predictor. And why do we do that? Feel free to read the answer from the screen. I try to encourage class participation any way that I can. Exactly. Why do we do that? Exactly right. Yeah, because and why is the intercept affected by centering? Back that up. That's implied by the slide, but not given.
Because when we readjust what our center is, we are essentially shifting up or down our line of best fit, for example, in linear regression. So if we shift our starting point along that, the intercept then either shifts up or down to accommodate that new starting point.
Exactly right. The intercept is the expected value when your predictors are 0, so it will change as a function of where 0 is. So somewhat of a segue into a different topic, but it's related in my head. Have you had a chance to look at homework 0 yet? A few of them? How'd it go? Any problems? No? Took about 5 minutes maybe? Okay, that's what it should be. You get 2 points extra credit for doing it. Throughout the semester, as you get to do real data analyses, centering is going to be checked by the system by asking for the fixed intercept in your models. Because if you have the intercept right, that tells me that you have the right predictors and that you center them correctly. If you get the slopes right but the intercept wrong, that means you have the right predictor but it's not centered at the right place. So there will be questions designed to make sure that you have the right setup before you get too far into the weeds of interpreting things, and the intercept is my checkpoint for whether your variables are coded or centered correctly. So yeah, we talked about that. We talked about different coding schemes for categorical variables too. That's kind of like centering, who's the 0, and how you can trick your model into giving you the mean differences across groups that you want to know, whether it's all relative to one reference group or sequential differences as you move up categories in an ordinal variable. Yes, indeed. We talked about linear combinations to get the missing group differences. We'll get some practice with that in example 1 and throughout the semester. So the model can always give you all possible pairwise differences across the categories of your predictor if you put in as many slopes as you have predictors, or categories, excuse me, -1. 1 is because you have a fixed intercept. If you were to leave that out, then you need as many slopes as you have categories. If you do that, you can get all the mean differences back, even if they're not directly given, because some are given as linear combinations. So in this example here, if we wanted to know the differences across the alternative groups, the treatment groups here, each of the slopes in the model tells us how each of these differs from control. But if the model gives us what the predicted mean is, we can work backwards to figure out what the difference must have been. So beta 2 minus beta 1, for instance, is how we compare the difference between groups 1 and 2. Beta 2 versus beta 3 here. Beta 3 minus 2 is how we would get 2 versus 3, and so forth. So we'll get some practice with that. We talked a little bit about lumping things together. So in terms of doing significance testing so that you can decide which effects are meaningful in your results section, you can test individual slopes and you don't have to do any extra work for that. On your output, there will be columns that say estimate, standard error. The next one over is going to be labeled either T or Z, but it is estimate divided by standard error. And then the next one over will be the p-value that goes with that corresponding test statistic. If you want to lump slopes together to get a joint hypothesis test of several things at once, you may have to write code to do that yourself. So you know this concept as these special cases, like the f-test for the R-square in a linear regression model. That's lumping all the slopes in the model together for a joint test of them against zero. If you do hierarchical regression, in which you have a set of predictors, and then you dump in another set of predictors, and you want to test whether the change to the model R-square is significant, lumping just the new set of slopes together gives you a test of that. Also, if you have, in an ANOVA context, as they call it, an omnibus main effective group, going back to this idea here, to answer the question, does treatment matter? Right, that's a more general question. I need to lump together all three of these slopes to answer that question, because it takes all three of those slopes to differentiate across my four groups. So that would be an F with three slopes lumped together. People would call that an omnibus or main effective group. And then you can get into specific group differences as you wish. All right. Then I asked about interaction terms. And that's where we can pick up. How's that sound? Anything I'm forgetting or that you'd like to ask about? Hello, Zoomers. Okay. Okay, it's still working. All right, it looked like my recording had stopped again. I was like, no! I can only re-give a lecture so many times. All right, then we're picking up on slide 18 with some vocabulary. So a thing that is very important to me is that you know how to interpret all of the numbers on your output. Not just in terms of significance and direction, but conceptually, how comprehensive a given effect in your model is depends on what else is in your model. So I like to use terminology to do this verbally, but then we'll also talk about how this translates given different types of models. So in our models, in most common models, the fixed effects, I say intercepts and slopes is what I'm talking about. I use the term fixed effects because they are constants. In other models, you can have things called random effects that are variables. So fixed effects specifically, they are either going to be some kind of expected outcome, which we usually call an intercept, or they're going to be some kind of slope. And we can talk about the slope that is differentiating categories of a predictor in the same way that we talk about it as if we're going one unit up on a quantitative variable. The slopes themselves have three possibilities in terms of how they should be interpreted, how comprehensive they are: bivariate marginal, unique marginal, and unique conditional. So if you have a model with one slope in it, we would call that a simple linear regression. If you have a model with one dummy-coded predictor, we would call that an independent samples t-test. Same damn thing. If there's only one slope, then that slope conveys the bivariate association between that predictor and that outcome. You can take that slope and turn it into a Pearson correlation, and it will be the same thing as the standardized slope in your model. So there's no after controlling for or conditional on, it's just period. This is the relationship between x and y. If you have more than one slope, then it turns into unique and marginal. So we have to say, after controlling for this stuff, here's the effect of my predictor. Or holding constant this other stuff, after adjusting for this other stuff. Any euphemisms I'm forgetting? How do we talk about this idea? Holding constant, controlling for, adjusting for are the ones that come to mind. What am I missing? That's the list? I got them all? On the first try?
I'm sure you could find some random paper, but those are the main ones.
Those are the main ones. That's too many words for me. I'm a fan of brevity when writing. Unique. That's what I say. This is the unique effect. Period. So the idea is that each slope conveys what that predictor brings to the table uniquely. If you picture the Venn diagram, the overlapping part gets kicked out, even though that contributes to the model R-square, it's still part of the prediction. But in terms of saying, who does this slope apply to, the answer is everyone. Like, this is the slope of how age predicts cognition in our example we'll do, period. Period. That's what the kids say right now. They put a T on the end. I've seen this. I'm not making it up. It's true. Okay, legit. This is the slope for everyone, period. I'm not probably saying it right, though, but I'm trying. So if the predictor is not part of an interaction term, then it's unique marginal. Applies to everyone. But if that predictor is part of an interaction term, then the terminology and the inference and interpretation switches to be unique conditional. This has a lot of synonyms. The one that is used most commonly that I really, really dislike is called a simple slope or a simple main effect. I dislike it because it is the opposite of simple. It makes it complicated. And I don't like to offend my readers by saying that things that are hard are simple. I did not make it up. I'm just the messenger. So to be a little more concrete, in a model like this, we're going to do generic first and then work our way into numbers and code eventually. I have an intercept and I have one slope for a variable called w. So my intercept is specifically when w is 0. I would want to make sure that 0 means something in the scale of w as a result. And beta 1 is the full bivariate relationship between y and w. It's equivalent to a correlation, essentially, if you were to standardize the variables. And it's marginal because it applies to everyone. This is the slope for w, period. If I add some more predictors to my model, beta 0 changes interpretation. This is now the expected outcome when w is 0, x is 0, and z is 0. So beta 0 is going to change because it means something different. Beta 1 is going to change because it means something different. This is now the unique effect of w after controlling for x and z. What does w bring to the table that these two don't have? Each of these is interpreted that way. What does x bring to the table that the others don't have? That's what beta 2 tells us. What does z bring to the table? But each of these is not part of an interaction term. These are what we would call main effects or marginal main effects. Marginal means applies to everybody. This is the slope of w no matter what your standing is on these other variables. This is for the whole sample. Beta 1 is one number and it applies equally to everyone. If I build in an interaction term, now I have x and z as part of an interaction. Beta 1 stays the same because w is not part of this interaction. So the way I would talk about beta 1 as the slope of w is what does w bring to the table after controlling for x and z, but that beta 1 slope applies to everyone. It's still marginal. Beta 0, new interpretation or same interpretation, as in the earlier models? Say it louder because you're right. Same. Why is it the same? Want to phone a friend? Get someone to help you? Okay, you're up. We're not friends. Ouch! Goodness gracious. You are now.
Why is it the same?
Why is the interpretation the same for this beta 0 as this one, even though we added an interaction term? That's the question. Do you want to phone a friend? Because we could just keep phoning around. That's
I
fine.
would just ask why would the interaction effect change the interpretation of beta 0?
It doesn't. What would have changed it? Why did it change from here to here?
Numerical added to the equation.
New predictor. That's the distinction. This beta 0 is conditional on W only. This one's conditional on W, X, and Z. This one is still conditional on W, X, and Z because when these things are 0, that thing is 0. So it's conditioned on the same things. Now, is the answer for what beta 0 is going to be necessarily the same? No, because this is a different model. This is a different prediction mechanism. So beta 0 may change in value, but it has the same interpretation. Likewise, beta 1 may change in value, but it has the same interpretation. It still is after controlling for X and Z, but beta 1 is the slope for W for everyone. Okay, Zoomers, you still with me? You get your ice cream, Vladimir? Feeling better? Yeah, ice cream makes everything better, I think, even in this weather. So long as it's not mint chip, right? That's a callback from the other class. But see, callbacks. Those of you who get to hang out with me all afternoon long, right, get the jokes in both classes. Now, what about beta 2? Same or different interpretation? It has to. Beta 2 switches to be unique conditional because the model now has the effect of X in two places. So beta 2 can't just be the effect of X, period. It has to incorporate this new piece. So it is going to be a different number and a different interpretation. Conditional is the idea that this beta 2 describes how X predicts Y only all by itself when Z is 0. That's when the new term drops out and you're left with just beta 2. So when is Z 0 is a very specific value on a continuous predictor or a specific group for a categorical predictor. So beta 2 doesn't apply to everybody. It's conditional. And that means that what this slope is dictated on how you centered the other variable, Z. I know this was coming, and that's why in my world we center everything from the get-go, because I want my parameters to mean interesting, useful things. Beta 3, same situation. It is now unique conditional when the other predictor is 0, when X is 0, because that's the only point at which the interaction term drops out, and we're left with just beta 3 as describing how X predicts Y. So we need X to have a meaningful 0 so that beta 3 means something. We need Z to have a meaningful 0 so that beta 2 means something. The tricky part is that it's the opposite one that you're worried about. Okay, with me so far? Now the interaction term itself. It's unique because it's controlling for W. However, it's marginal. This is the interaction term for everyone. Can you think of how it might become conditional in another model if I had room on the slide to keep going? What would it take to make this interaction term conditional on something?
We would need another interaction term that would also include either X or Z or both.
Yep. If there were a three-way interaction in which X by Z was two of the ways, then this is conditional on the third thing being 0, and it would be conditional. In this model, it is unconditional because there's nothing that contains both X and Z at the same time. Okay, so the way that we talk about beta 4, though, is not the same way that we talk about beta 1s, 2, and 3. Here are the rules that I'm going to teach you. How do we talk about interaction terms? We talk about what happens to their main effect slopes instead. We do not talk about what happens to Y. It's a trickle-down situation. In this example, beta 4 has two equally correct interpretations. You can pick the one you like, or that corresponds to your research question more directly. We can talk about it as X as the thing we care about, and Z as the moderator. If we do it that way, then we would say beta 4 is how beta 2 changes as Z increases. Not how Y changes, how beta 2 does, the other one. Z could be the predictor instead, and X is the moderator, and then we would talk about how beta 4 changes beta 3. There is no mathematical way to say which predictor is the predictor and which is the moderator. That is entirely a substantive distinction. Up to you. So how we can figure out then, using the model, what beta 2 would be for a different level of Z and what beta 3 would be for a different level of X is a 3-step process. Number 1, what slope do you want? Go into the equation, find the terms that contain that variable. That's step 1. Step 2, factor out the variable the slope is for. Step 3, the answer. So for instance, if I care about the slope of X, and that's what I want to figure out, I go into my model up here. Is there an X in here? No, I don't need beta 0. Is there an X in here? No. Need that one? Do I need this one? Follow my mouse here. I do not. Do I need this guy? Need this one. Okay. So I've isolated the terms that have the variable, the slope I'm interested in. I then factor out the common X. So X goes behind. What's left in the front in brackets is the ingredients by which the model is going to tell me for any level of Z what the effect of X is going to be. And this makes it a little more clear why beta 2 is only when Z is 0, is because that's when this latter part drops out. If I want to go the other way, then I have Z as the predictor I care about. I go into my model, I grab all the terms that have Z, they have to have Z, bring them down here, factor out Z because that's the predictor I care about, and what's left is how I get the model implied slope for any level of X as the moderator. You can do this using any software package. It's called Estimate in SAS, Lincom and Stata. There's a GLHT package I use in R. In SPSS, under the mixed model package, it's available as test. Under the regression side, I think it's called Matrix or something. Every software package has this. In M+, it's called new with the model constraint statement. So I will teach you how to do this. Lots of interaction terms this semester and in higher order models as well. So, okay, with me so far? So you can talk about the numbers all you want, right? You can write your results section and interpret beta 4. But at the end of that, you're going to need to write some English so that the people reading your paper will do the yellow highlight on that sentence. Or Spanish, whatever language you're writing in, right? But words and not stat-ease is the idea. The good news is that there are only 4 kinds of interactions, and once you figure out which kind you're in, it gets a lot easier. Because the interaction term moderates each of its main effect slopes, we will talk about it taking one of those slopes and making it more positive, less positive, more negative, or less negative. Those are the only choices. If your answer starts with more, that is a stronger effect as the moderator increases, or what people call an over-additive interaction, where additive just means main effects all by themselves. If your answer is less something, then the effect is weaker as the moderator increases, and you have an under-additive interaction. So if I have this model again, same idea here. If my slope of X at beta 2 is 10, let's say, and the beta 4 coefficient for the interaction term between X and Z is 2, then the way I would talk about this is for every unit higher Z, the slope of X that was 10 becomes more positive by 2. So in people that have higher Z, X matters more. That's what more positive means. Higher X relates to higher Z, higher X relates to higher Y, more so in people with higher Z. That's my sentence. If I have a slope of 10 for X, so higher X relates to higher Y when Z is 0, but the interaction coefficient, beta 4, is negative 2. Then I would say for every unit higher z, the slope of x becomes less positive by 2. And that is the way I would say it. Not lower, less positive. Because if I have a z of 1, my slope becomes 8. That's still positive. That's still a positive relationship. Real-world example of this, the first line, tomorrow will be warmer than yesterday. In the summertime, when it gets colder, they don't say it's going to get colder. They say it's going to be not as warm. Because that's not the same thing, right? Midwesterners will go outside today and say, it's warm. Narrator says, it is not warm. It is 35 degrees. But relatively speaking, it's warmer. I would call this less cold, quite frankly. This is what it is. It's less cold.
Yeah, no, we don't measure cold, we measure heat.
I know, right? Less cold is more like the bottom one here. If my slope is negative 10 and my interaction term is 2, then as x goes up, y goes down. Less so if I'm higher on z. The slope becomes less negative. So I would call that not as cold. And then if you have negative 10 for the slope and negative 2 for the interaction, that's in the more negative. So it's stronger. Those are the rules. Once you figure out which cell you're in, you're home free. So I like doing it this way, not higher or lower, because that's ambiguous. Direction, and then which way is it going as the moderator increases. That's the way that I typically approach this. Okay. How are we doing? Thumb test? Positive? Zoomers, want to play? They're thumbing up too. All right. Switching gears then. Let's do a little practice. This is the new stuff that I posted. It's blue because it's from the intermediate class. I'm actually going to keep this open so I can type. And if you want, I can post the completed version after class, so you don't have to type along with me. Would you like that? Okay, done. I'm all about customer satisfaction here. I don't bring pizza on evaluation day, but I will do the things that I can, like post the handout when I'm done typing in it. So this is the slide that I pulled up last time. If I can get more on the screen here. This is a hypothetical example, but I wanted to put some numbers in. So Y is student achievement on a percentage scale out of 100. X is some measure of the importance of education on a 1 to 5 scale, so an ordinal measure like we would typically see in the social sciences. Parent education in terms of number of years. Okay. And I put my predictor variables in the model. I think that the effect of having more educated parents is going to be enhanced in people who think education is important. That's my hypothesis. Okay? I'm right. This is my world. I made the interaction term positive. Now let's write up our results section. Beta 0 is my intercept. What's it mean? I'll start you off. Expected. What's my outcome? Yep, feel free to read from the screens. When, or let's go for. What kind of person? Zero attitudes, which can't help it happen. That's not a choice. And 0 years of school. Could happen. Unlikely that a person who's never been to school is going to be in my research study, especially if it involves reading. All right, so that explains why my predicted GPA is 30. This is a child that does not exist. But it's the constant. Nobody cares about the constant, right? That's why it's at the bottom of the output in Stata. I'm just full of snark today. I'm sorry. I'm on a roll. All right, beta 1. This is the slope of attitudes. Do attitudes enhance GPA? Okay, so how do I type this?
The expected increase in
Yeah.
GPA.
Okay, so let's go with, yeah, increase, sure, in GPA.
For a 1 unit change in attitude.
Yeah, I'm going to go per unit change, make it shorter, in attitude,
Holding years constant.
holding years constant, and constant at what?
No
In
idea.
this case, 0.
Yeah, for ed equals 0. Not just holding constant at 0 specifically because of this interaction term. So should I be excited that I got my positive slope I hypothesized? And it applies to people I don't have in my SETI? Probably not. 0 for 2 so far in meaningful interpretations. Let's keep going. I'll start this one off for you. Increase in GPA per unit change in, what's my variable this time? Ed for
Attitude 0.
attitude 0. Also can't happen. 0 for 3, folks. This is why centering matters. How about the interaction term? So if attitudes is the moderator, then I want to focus on what happens to this slope. So I don't start the sentence with increase in GPA. I start it with increase in ed slope. Okay, increase in this specifically. Per unit change in what? Yes, for the other one as the moderator. Per unit at. I'm going to abbreviate since I'm out of space. Now, do I have to say specifically for attitude 0 or something like that? No, because it's marginal. This interaction term applies equally to everybody, unconditional. This is conditional, or a simple slope, as it is called, or a simple main effect. This is conditional, simple main effect. This is marginal. Now, what if I want to tell the story the other way?
You swap attitude and ed.
Yep, increase in at slope. Almost can type. Per unit ed. So of the 4 kinds, more positive, less positive, more negative or less negative, with respect to attitude as the moderator, which kind is this? With respect to the other one as the moderator. Yeah, this one's unambiguous. So the slope gets stronger as you move up the other variable, is the conclusion. Matters more is the way that I like to say that quickly. So even though all of these make no sense, there's nothing technically wrong with this. Because the model still predicts the expected outcome for any kind of person, and it still predicts the expected slopes for any level of the moderator. So I can use this equation and fill in better values, for instance. What if I have somebody who has a 3 on attitudes, so mid-range in terms of importance, and a high school education, 12 years of education? Then I plug in the coefficients multiplied by the values of the predictors that I want here, and I come up with a predicted GPA of 75. So the issues with centering is not about R-square or prediction or fit or any of like that stuff. It's literally like, do the numbers tell you anything useful? And I like them too. I prefer that. It's less work. I prefer to do the work on the front end with the centering rather than on the back end. Okay, how are we doing? 2 thumbs up. I'll take that. Questions or things you want to hear again? Still checking my recording is still working, hopefully.
Lisa, do you have a slide that talks about, right, so we're getting this slope essentially for ed slope or attitude slope, depending on which way you're talking about.
Yep.
It took me a while to understand that that was like talking about the slope and not like a predicted value.
Mm-hmm.
Do you have a slide that kind of shows that in your lecture?
I had something on how to make predicted values, but I decided to take it out because I figured that was something that folks should already know. But if you have ideas for what that could look like, please tell me. Like, what are you envisioning?
I don't know.
You don't know?
I'll think about
Okay, yeah, let it percolate, and maybe I'll make one. Because, yeah, why not, right?
I think it could be helpful if you had a plot and it was just two ways. So let's say we're using education as the moderator.
Okay, education is the moderator.
On the x-axis, you just have attitude. And so you could have different lines showing different values for education.
Yes, I could, and in example 1, I do. Yeah, because these aren't data, these are just numbers. But yes, we will get there, because that is like your reader's like, what? Can I just see a picture? Especially for interaction terms, pictures are essential. They absolutely are. But to make the picture, you have to generate predicted values. And in order to talk about your relationships, you need to know who they're for. Because you can't say attitudes matters when maybe for some part of your sample it doesn't, because the moderator's cranking it back down. So that's why this matters to me, is because I don't want you to look at these main effects and draw universal conclusions about what matters and what doesn't, when the model is conditioning that on every other thing. Because you will see these things switch sign, switch significance as you add interaction terms, because they don't mean the same thing. That's the thing. So what if I decide to center my variables ahead of time? Here's my new equation. And when I write equations in examples and in real papers, I like to show the centering in the equation explicitly, so my reader knows what 0 is without having to read. So I figured out on the previous slide that the predicted GPA for somebody with an attitude of 3 and education of 12 as my new reference point was going to be 75. I know what the other slopes are too. How did I do that? Sorcery? Lucky guess? The 3-step process. Find all the terms that have the thing you care about. Factor the predictor that you care about out. What's left is the ingredients. So we'll work through that in just a second. But now, if this is my model, how do I start my results section? Expected GPA, when or for?
Or attitude equals 3 and education equals 12.
Yep. That person might be in my sample. Or that sounds like they plausibly could be. This used to be 1, now it's 7. So this is change in GPA per unit at, am I done? For whom?
Add equals 12.
That's right. 4. There we go. Likewise, change in GPA per unit ed for, yep, 3 for 3 with meaningful effects at this point. Now, does beta 3 change? It's the same. Because this describes how the slopes increase as a function of the other variable, it's still there. The difference is the reference point for that increase to apply to. We're starting up higher on the variables this time. So yeah, my conclusion is the same. These slopes are still positive, but they look a lot stronger in this case. So here's how we figured out what those new slopes should have been. What it is plus what modifies it is my shorthand. Identify the terms, factor it out. So here's that math. So if I want to get the attitude slope, I go into the equation and find all the terms that have attitudes, and I've color-coded it to make it a little less painful. Not too big. So I need beta 1, and I need the interaction term. That's step 1. For the education slope, I need beta 2 and the interaction term. I then factor out the variable the slope is for. So attitudes goes behind it in the first one, education goes behind it in the second, and the stuff that's left in the brackets, that's my equation. What it is plus what modifies it. To get the attitude slope, you start with the attitude slope, then you figure out what modifies it. Same thing with the education slope. So note the interaction term in here. See, I see extra little spaces and they're bugging me. I am that picky. Note that the interaction term is being multiplied by a different variable in each of these cases. It's doing two jobs at the same time. So I can get my calculator out and figure out what this estimate is going to be. If I want to, I can keep my calculator out and find the standard error of the new linear combination. The standard error squared, or its sampling variance as we would call that, is the standard error squared for beta 1 plus the standard error squared for the interaction term as a multiplier of the value of the moderator that you want the slope for, and then the covariance between the standard errors for these things. Now this is a simple formula because this is a simple case. The formula gets uglier the more stuff the model has in it. So ask the software to do it for you is what we're going to do. We're not getting our calculators out. We're not doing that. That's not reproducible research. So how do we do it? This is the thing that I did not learn until I was on the tenure track, and I'm going to make sure you learn it well in advance of that, or any other career that you see yourself in. How do I tell the software to make that linear combination for me? So this part, here's my model, is stata code for LinCom. So this is like fill in the blank here, so we can get used to the logic of how these statements work. The exact same thing happens in R in a much more I would say convoluted and less transparent way. How's that? So in stata, comments are green, but it wasn't showing up, so I turned it gray. What if I want to get the attitude slope for somebody who has a 10th grade education? It's not going to be this one, right? Because this one's for 12. But I can ask for it. So here's my ingredients for how I get the attitude slope for anyone. In these statements, what you are putting in the blanks is the multiplier. So in this, how many beta 1s do I need? I just need 1, because that's where our starting point is. So when I see attitudes here, what it's actually doing internally is saying, hey, I'm going to replace this with whatever beta 1 is going to be estimated to be. So beta 1 is actually right here. That's what the words mean. They refer to the estimated slopes. And then next, you provide a multiplier. I need 1 of those. You don't actually have to type the times 1, but I do it to keep everything sort of obvious. In SAS, you do have to write the 1 in the way doing it. I took the SAS out of this, but the older version of this class has it. Okay, now here's the tricky one. This is where everybody screws this up, okay? Cough, cough, homework, help. What goes here? 0, okay. Why 0? That's exactly right. People are like, but usually they're thinking, well, I want it for ed equals 10, so wouldn't I put that here because this is ed? No, this is beta 2. Beta 2 has nothing to do with the slope of attitudes. It is not part of the story. So yes, this is a 0. You don't have to include it in your statement at all. Now what goes here? How many beta 3s do we need? -2. Because our variable is centered such that 0 is 12. So if we want it for 10, it's -2. This is another thing people screw up, is they put in the original values and not the centered values. It has to be the values as the model has processed them. So if I submit this line to Stata with the word lincom in the front of it, in lowercase, of course, then it will spit out the model implied attitude slope estimate standard error hypothesis test. Confidence intervals too. Okay, want to do another one?
So what is the pound sign?
Oh, # is Stata code for interaction term. You don't have to literally create a new variable that is the multiplication of the two. You can do it on the fly. It's # or hashtag. I was waiting for someone to say hashtag, but in Stata. In R, it is a colon. In SAS, it is an asterisk. In SPSS, it's an asterisk. You can do that in all these packages under a GLM or generalized package. Okay.
You might see a double hashtag in Stata code.
Yep.
That gives you the interaction and then all of the lower order slopes.
Yep.
And yeah, so in our example that we have here with GPA and these things, you could put in,
Like that.
yeah.
So if you put just that in to your model,
Yep, so it'll include the interaction and then it'll include the attitude slope and the education slope without having to put it in like your action. It's a shortcut to like reduce your code.
you're typing.
Yeah.
And if you had 3 variables and you wanted a 3-way interaction term, one more, and you get all main effects, all 3 2-ways, and 1 3-way. I deliberately hide that from people when I start teaching this because I don't want them to like forget the lower order terms, and doing lots of typing is a good way to reinforce that. But once you get sick of typing and you know what you're doing, absolutely. So I do not do that on purpose in my examples. Okay, want to do another one? What if the attitude slope was, what if we want the attitude slope for education equals 18? Now I've put the constant to 0 for you, because if your question is about a slope, the intercept will never ever have anything to do with that. Okay. What goes here? How many beta 1s do we need? How many beta 2s do we need? How many interactions do we need? How many beta 3s do we need? 6. Y'all got this. Okay, this is Stata. I like the fact that everything is next to the words, so you don't have to remember. R folks, this is what you get to look forward to. You get to fill in blanks that are in isolation, and you just have to know, based on the order of the terms in your output, what the multipliers are. In your output. Okay, I've made this mistake. I like to include interaction terms right after their main effects and then maybe more predictors. And whenever I do that, R rearranges it so interactions are always last. I have not found a good workaround for that, although I believe it to exist. I just haven't found it. So it's the same numbers that we're going to put in these little blanks. You just have to use the context of your output to say which one. So this is, I need 1 beta 2, I need 0 beta 3s, and I need -2 beta, 1 beta 1, no beta 2s, and this many beta 3s. Likewise, this one would be this, and 6. All right, now let's go the other way. What if my focus is on the slope of education and attitudes is my moderator? Do I need an intercept? Nope. How many beta 1s do I need if my focus is the education slope? I need none of them. We're working from this as the ingredients here now. How many beta 2s do I need? How many interactions do I need if I want the edge slope for attitudes being 2? This is -1. So the interaction term here is tricky because the first 2 times through, it was like the at part got set to 1, and we filled in what we wanted ed to be. The next 2 times through, I'll go ahead and complete the puzzle here since y'all are getting it. What goes here if attitudes is 5?
2.
Very good. So the first 2 times through, I am filling in what I want ed to be as the moderator. Now I am filling in what I want at to be as the moderator. That's the tricky part. And then down here, finishing it up, 1 of those, minus 1 of those, that. Excellent. We got it. How are we doing? 2 thumbs up still. Any that you want to hear again or ask more about? Yes, I know. I'm of that kind, okay? Having your code equally spaced and using a fixed width font makes your code much easier to read, and especially when you get into these, like when you have 8,000 of these in a row and they're not aligned, like don't do that to yourself. Take the time to space it, it will help you. So these are arbitrary, right? Like these are just, what if it was 10? What if it was 8? You could conceivably compute simple slopes for every different value of your predictor if you wanted to. Sometimes it's limited by what is available in the moderator. So let's say that I have a model where age is in here. I have a binary indicator for biological sex, which I'm calling woman, meaning that 0 is dudes and 1 is chicks. I have my interaction term. So what are the ingredients here that I need to calculate an age slope? If I want an age slope, step 1, find the terms that have age, right? Step 2, factor out the variable the slope is 4. So what goes here?
Beta 1 and beta 3 times 4.
Yep. If I want the gender slope, do I need beta 1? Nope. Do I need beta 2? Yes, I do. Do I need beta 3? What does it multiply? And don't say W. Yeah, the age one. Like that. Okay. So if this moderator is a binary variable, then there's really only 2 possibilities in terms of what I would care about. What's the age slope in this group? What's the age slope in that group? The end. If I want the, let's do these real quick. What goes here? Yep. What goes here if men are the 0 and women are the 1? And I want this for men?
2.
Did it matter? Does this ever change if I'm talking about the age slope? Remember, this refers to beta 2. Yeah, it never changes. Will this ever change if I want the age slope? No, it always starts with the one you want, and a 1. Okay, put that there. What goes here if I want it for a man? What goes here if I want it for a woman? There. That was a little less dramatic than I wanted. Come on, the space over, man. Thank you. Okay. Now, what about the other side? What if I'm interested in gender differences? Well, these are old people. If I'm centering at 85, I could do it 70, 80, 90, 100. Is that useful to compute like 7,000 slopes? Probably not. What I really want to know is like for whom is there a gender difference and for whom is there not? So a way to do that I think is super cool, called regions of significance. I can put this back to big again. Or what is it? What did we talk about? Johnson-Neyman. So this was something from like the 1920s that people figured out how to hack for this purpose. I call it regions of significance. Basically what we would want to know is the value of age at which the gender effect turns on and the value of age at which it turns back off again. But if an interaction term is creating non-parallel lines, then that guarantees it's actually going to flip at some point. There is some point at which the difference between men and women will be positive, some point at which it narrows to 0, and then the lines are going to cross, and it's going to switch, and the difference will be negative. So we can figure out where those points are. So if we know the estimate for a slope, and divide that estimate by the standard error, we know the t-value, and we know that significance starts, if we're ignoring degrees of freedom, with a t that's greater than 1.96 or less than negative 1.96. We know that. So we work backwards to rearrange the formula to find what value we need to make t hit this cutoff. So the computations for this part you know. We also need to get the standard error for it, and to be able to compute that, we need access to the asymptotic covariance matrix, basically the covariance matrix of the standard errors of your fixed effects. But once we have those pieces, we can run the computations. There's an R package for this, I wrote a SAS macro for this, and I have a spreadsheet that does this. So there's various ways to do this. Do you know of any Stata packages that do this, top of your head?
But I also haven't.
Yeah, I'm sure there is one, because Stata has packages that people write just like R does. They're called ADUs. So you can find some person who's made this and use their code. So in this example then, if my results, and this is from, I think, chapter 2 of my book in that data set, I have it in there. So beta 2 in this model is the gender difference is negative 0.53 for my outcome. So that means who's higher, men or women, if the slope is negative and 0 is men and 1 is women? Who's higher? Men. So it's a gender gap that's favoring men, conditionally at age 85. All right? So I have the standard error for that. The interaction term is negative. So what does that imply about the gender gap as age increases? Which pattern is this? This negative slope, does it become more negative or less negative? More negative. So is the gender gap growing or shrinking in older people? Growing. And that's the kind of language I would use. Your readers are not going to be here for more negative. But the gap is growing is something that people can hang on to. Or the benefit for dudes is better in older dudes. Maybe not dudes, but you get the premise. So then the question is, like, okay, at age 85 it's significant. It's going to get bigger in older people. At what point is there not a gap, right? Because if it's becoming more negative as age increases, it's becoming less negative as age decreases. So we can figure that out with the formula. And I did the stuff, and this is what it works out to be. So the region of significance for the moderator of age is 60 to about 80. So that's saying that the gender effect is predicted to be significantly negative above 80, so which includes the centering point of 85. It becomes non-significant from 80 down to 60, and then 60 is the point where it starts heading significantly positive in the opposite direction. So for my sample, I need to know, what is the age range? Do I have 60-year-olds in my sample? Because at that point, we would expect the opposite gender effect to be significant. And in chapter 2, I did some analysis of this, and it worked out to be that like half the sample would have a significantly negative effect and half would have a non-significant effect based on the distribution that we have. So I like this a lot more than just what would it be at 80? What would it be at 90? Because then this is a little more principled. So this is some cool stuff, I think. I think it's cool. So I'm going to show you how to do all this stuff. What do you think about that? Doing stuff is important.
When we're talking about the region of significance,
Yes.
you listed that 60 to 80 range.
Yes. That's what came out of the computations.
When we're interpreting that, wouldn't that be the region of non-significance or insignificance, however you want to phrase it?
Non. It would, yeah, so there's two regions, basically. There's where does it flip negative, where does it turn to 0, and where does it flip to positive in terms of significantly so. So it's a region across the whole thing. But regions of significance would be like how much of it is positive, how much of it is negative. But yeah, in the middle it's non-significant. So yeah, I guess if that'd be a more pessimistic way to look at it is what's the region of non-significance? But people usually don't phrase their questions that way. But your point is well taken. So this isn't so bad, right? Right? This wasn't too bad. It's algorithmic, right? Once you know how to do it, you just know how to do it. What about more than one interaction? This is slide 22 in the original lecture one. I had x by z here. Now I'm adding w by z. So w, x, and z is part of my generic story here. Because w is now involved in this interaction term, it switches to become unique conditional as well. This beta 1 is now the slope specifically in people of a z of 0. So beta 2 is the slope of x. It's only conditional on z of 0 because it's only part of this interaction. But beta 3 is doubly conditional. Z is here and here. So now beta 3 is specifically for 0x and 0w.
And do we not need to specify, so for example, for beta 1, do we not need to specify holding x constant in addition to that, or is it just implied or assumed?
Constant at 0
Well,
is what I
z
would
is
say.
constant at 0, but
The-
x,
The slope, so for beta 1,
right,
then this is holding x constant and z constant at 0.
okay, so we don't need to add the extra word saying, okay.
Yeah, and I usually, I don't holding things constant. I'll say that once. All slopes are interpreted as the unique effects holding other predictors constant. That's one sentence, and then I talk about it. But constant at 0 is different, and I do make that point. Like, who is this slope for? The z slope is for these two being 0 at the same time. The interactions are still marginal because there's nothing that has both of them in another term. So beta 4 has a different interpretation, or excuse me, beta 4 is unchanged. It's controlling for beta 5. Beta 5 has two equally correct interpretations. It's how z makes the slope of w more or less positive or negative, or how w makes the slope of z more or less positive or negative. Either way. So then if we wanted to find the model implied slope, the rules are the same. What variable do you want the slope for? Find all the spots that have it. Take them down. Factor out the variable you want the slope for. What's left is the answer. So for things that are only conditional once, that's what we just did. The new one for z, doubly conditional, z is here, z is here, z is here. So our answer has to involve beta 3, 4, and 5. So now we start with what is the slope for z when these things are 0? How does it change as a function of x? Plus how does it change as a function of w? Same principles. And you can do, this is regions of significance. Here's an article on your reading list about it. Gives some R code and some pictures and things like that. So for these sorts of quantitative variables, we can find the ranges at which these things turn on and off. All right. I think that's good. But you see where I'm going with this? Foreshadowing next time? There we go. What if I have a 4-group predictor and I want to know if the effect of age varies by group? How many new interaction terms do I need to answer that question? If group took 3 slopes in the first place, how many slopes is moderation of group by age going to take? 3. Yep, that's where we're going with that. Your first homework assignment is going to make you do this. Sorry, not sorry. But guess what? I'm here to help. Vladimir's going to be here to help once his face heals better. Nikki's here to help. It's going to be okay. It's the golf homework.
Yes.
You like that one? All right. They're legendary, but I think it's good for now. I'm actually headed over to the stat department to see a talk this afternoon, so I need to end class a few minutes early so I can do that. That's all right. But this is a good stopping point. So, questions? Anything as we wrap up here? Okay, then let's see. It is Thursday, which means I say, have a good weekend. Let me know if you need anything. Do homework 0, and I'll see you next week.
Office hours on Friday.
Yep, office hours on Friday.